I mean, EMG is nothing but gives information about muscle contraction, right? You can see for a same activity, we can see different patterns. You can see for same activity, different patterns. Okay, again, this cannot be directly used for control purpose because for a same activity, you should get the same signal, right? No, we will not get the same signal, and we will see what are the, let's say, fundamental reasons begin that, and why we do signal processing. See, basically, we are all signal processing, and even though the title is human machine interface and rehabilitation engineering, we do signal processing to decode, let's say, the movement interest. Okay, if we do EEG, which means EEG based receive brain computer interface, which means we are decoding the brain activity. And here, if we use EMG, then which means we are going to decode the muscle. Okay, so that's a thing. Okay, here. It's fine right now. Okay, so yeah, see, this is the basic control mechanism, right? No, as I said, see, whenever we do movement, okay, see, in this case, see, I mean, let's say in this case, the person is trying to hold the ball, right? No, see, here, this activity, if you see this activity, not to complete this activity, okay, this muscles alone, will not be sufficient. Okay, see, the entire system is involved. See, brain is involved. Brain gives commands to the muscle, and see, again, from muscle some feedback information is going. Okay, and based on that, this the activity is completed. The it's a closed circuit. Now, let's say in amputees. See, amputee means I mean, when a person undergoes some sort of amputations, okay, it could be, let's say, due to several reasons. One, one, let's say, common reason is accidents. Okay, due to accident, if you see somebody is, let's say, losing their leg, or let's say fingers, okay, or let's say hand, or let's say, some, let's say, part of the hand, okay, those are all, amputations. I mean, if this happens at a hand level, then we say upper limb amputation. I mean, the prosthetic hand gets basically what we have signals of muscles. I mean, sorry, we have signals from the muscles, but now with that signal we decode the information and we actuate our prosthetic hand to carry out this function. So that's a
the overall picture. Okay. So here, as I said, like ultimately, like the force is different. See, same task, but we need different force. Okay, and this force generally what like dependent on two important factors. Again, little bit of physiology, modern recruitment, modern. I mean, see, we have muscles. Okay, see, we have small muscles and I mean big muscles. So big muscles in the sense I have like more number of motor units. Small muscles I have, let's say, less number of motor units. So how many motor neurons, sorry, motor units are involved in the task? Okay, or recruited for the task is nothing but motor unit recruitment. Firing rate means number of times it fires. Okay, so this is I think it's not okay. So yeah, so this is what this is actually the this thing. I mean, if we try to let's say visualize the entire picture in terms of mathematics, okay, we will have something like this. Okay, see, we have spinal cord. Okay, spinal cord. Okay, and generally, like I mean, nerves starts from spinal cord and it innervates to muscles. So let's say it just starts from spinal cord and it goes all the way to muscle. Okay, so it gives signal. So I mean, see, these are all the signals. Okay, these are all some impulses. Okay, and we will get like different signals. See, this is again I mean, like signal from one motor unit. This is signal from another motor unit. This is signal from another motor unit, and in fact muscle contains n number of motor units, and your EMG is nothing but like summation of the all I mean summation of I mean it's nothing but arithmetic summation of motor unit action potential trains. Okay, so this is what, like, see, I mean your signal will be looking like this. Okay, so and generally the noise, I will come to that. Okay, why we have noise? EMG will be looking like this. Okay, and I mean we have different. I mean we have different types of EMG. Particularly surface EMG, doctors consider that as a noise. Okay, we'll see in a while. Next, இது work ஆக மாட்டேங்குதுங்க. Next. Okay, so yeah, so this is the physiology. Yeah, yeah, okay. Next, next. Okay, fine. So, so we have learned about EMG, right? I mean, sorry, muscles, and we have also discussed about how EMG looks like. Okay, EMG, how EMG looks like, right? No, so generally, I mean, when we design a system, let's say when I mean, let's say like we have to come up with a system that should capture this signal. Okay, what are all the components we can have? Any electrical engineers, biomedical engineers? Okay, see, the task is very simple. See, I know that like my muscle, whenever my muscle contracts, I'll get some signal. Okay, now I want to capture, I mean I want to come up with a system that should capture the signal. Then what are all the components this system should have? Electrodes, great, right? No, first thing, electrodes. Because see, why electrodes? To sense the action potential of the muscle. See, okay, see, inside the body we have body fluids, right? No, body fluids. Okay, and if you want to be very precise, we have ions, sodium, potassium, chloride. Okay, so what this electrode should do? Your answer, you are correct. Mm-hmm. 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 So see, inside the body we have ions. Okay, Okay, outside if you see any electronic device, okay, I mean let's say any electronic circuits, okay. See, I mean outside if you see the this thing, okay, if you want to measure voltage change, then definitely there should be what flow of current. Inside we have ions. Okay, see inside the body we have ions. Outside, for example, any system, okay, any electrical system, if you consider, okay, you have current, you have resistance, you have voltage. Okay, and yeah, of course, like you also have capacitors, impedance, and but these three are like very basic parameter, right? No, inside we have ions. Okay, see this electrode, what it does, you might have known about Nernst potential, Nernst equation, sorry. Okay, see Nernst equation, what actually Nernst have done, just now he came up with the relationship, okay, between the ionic potential and electronic potential, or let's say electric potential. Okay, see outside the system what we have, okay, see in order to flow current, then like there should be what, like change in the flow of electrons, but inside what we have ions, so the flow of ions should be converted to flow of electrons, right? No, so this electrode basically is a transducer, okay, that converts the ionic potential to electric potential. Okay, very important. Okay, and I'll tell you why it is important. See, I mean, like in our case, we consider human body as a source. Okay, human body as a source. So you are going to place instrument, instrumentation system on a human body. Okay, and there is an interface. Okay, so now what, see I don't want to, when I capture some signals from the human body, see I don't want to have any loss at the interface, or else see ideally loss would be 0, but it cannot, it cannot, it is not possible. So what actually we can do, we can make as minimum as possible, right? No, as minimum as possible, and for that purpose, generally, like you see, that's the reason, like some of you, either you would have given your ECG, or else you would have seen some of your friends or relatives giving ECG. Nurse staff, like they will be applying some gel. It contains what, like Cl, Na plus Cl, okay, ions. So basically, that actually reduces the impedance that, like that are developed at the interface. Okay, so that's this thing. Okay, in fact that's one of the drawback, I'll come to that later. So basically, like we have electrode, okay, that actually, it's a transducer that converts ionic potential to electric potential. Then we next yeah, so we have instrumentation amplifier. Okay, here another, yeah, we have instrumentation amplifier. I mean see the signal that we are interested in, let's say capturing, that are all, like very what low in amplitude. Okay, in terms of because you remember, like I said that, like muscles, above that we have skin. So the skin, if you see, whatever the signal we intend to capture, okay, that signal should propagate through the skin. Okay, again there will be some drop. Okay, you got my point. Then another drop, okay, happens at the interface. Okay, so obviously, like we will expect, like the voltage to be as low as possible. So one this thing is, like we use instrumentation amplifier to improve the gain, so that, like the signal will be amplified, and at the same time, because like we have very good common mode rejection ratio. Okay, which means, like we'll have very high differential gain, very low common mode gain. Okay, I don't want to get into too much details, but generally, like instrumentation amplifier, like mostly we use for any bio if you design any biomedical signal conditioning circuit, you cannot avoid instrumentation. Okay, next. Yeah, so filters. See, one thing, like even we see now, okay, whenever we perform measurements, biomedical measurements, okay, you cannot avoid interference from, let's say electromagnetic field, okay, EMF. So the interference due to EMF, we cannot avoid, okay, and that is one thing, okay. I mean that usually creates, that's a source for your power line interference. Apart from that, see, when we see we are going to show electrodes. So when I place, I mean when I let's say when the subject attach the electrodes, and if they are running, okay, then that also creates some disturbance to the measurement. See, already your measurement variable, that is characterized by low amplitude and low frequency, and and it does not mean for example, then in that case, we will ask which means when I perform measurement, I should not move. Then that's not at all possible. For example, in sports, okay, I want to measure the performance, during the training, let's say. I cannot ask my athletic person to sit, and I cannot measure his or her performance, right? No, so that's another. So that I mean this thing. I mean when we record activity, the movements, okay, also disturbs your measurement. Okay, that is that actually that contributes to this thing. I mean movement artifact. Next, so for that purpose, we have low pass filter. Generally, next, yeah, you can see, yeah, cutoff frequency, no, yeah, low pass filter. Next, high pass, again, we also have some high frequency noise, okay. So to remove high frequency noise, we have low pass filter, sorry, and to remove low frequency noise, we have high pass, okay, right? No, okay, fine. So by the way, what is missing here? I think one important component is missing. Now that we discussed. See, yes. No. See, I mean, see, let's say what we are discussing. Let's say somebody is coming to us and they're asking us to design an EMG system. Okay, then definitely what question we will ask? I mean, okay, fine. What could be the amplitude, range? Then what could be the frequency? Okay, you got my point. So what could be the frequency? Why we want to know the frequency? Why we want to know the frequency? Yes, what is that? Nyquist criteria, anti-aliasing filter. Right, no, anti-aliasing filter. Right now, for example, in our case, see, EMG frequency is 500 hertz. Okay, EMG frequency is 500 hertz. Then, I mean, when I record, okay, which means 500 hertz means I mean, what the useful information we will get from EMG is up to 500 hertz. Okay, after that, I mean the frequencies above 500 are considered as noise, or let's say unreliable information and so on. So generally we will ignore that. Okay, so in that case, so I mean when I this thing, okay, when I design, first I have my anti-aliasing filter, okay, and what could be the frequency range of anti-aliasing filter? If let's say my desired frequency is 500 hertz, minimum frequency இல்லப்பா 500 hertz, signal 500 hertz. So நீ 10 hertz na எல்லாம் போயிரும் இல்லையா? So according to the Nyquist criteria, it should be at least twice, right? No, so it should be at least 1000 hertz. Okay, you got my point. So I mean you should have a low pass filter, okay, that passes up to 1000 hertz. Then we have to do all this, okay, gain, I mean amplifier, I mean what, your instrument is amplifier, then low pass filter, then high pass filter. So first we start with anti-aliasing, so that we are ensuring that the signal what we are, the signal what we have in our hand, okay, it falls in the desired range. Okay, that's the thing. So, I mean, technically it should be twice the this thing, the maximum frequency. But I mean, if you practically try to implement, like generally we choose 4 times, 5 times, okay, of the maximum frequency. Okay, next. So these are all. So yeah, number of bits. I'll come to that. Anyway, this is too much technical. Okay, next. Okay, yeah. So yeah. Just a minute. So the moment EMG is EMG we have. Okay, how do we control? I mean, how do we use this EMG for control is what we are interested in. We'll see. See, this signal, not only be used in, this thing, I mean, control purpose. Apart from that, it is also useful in what, like sports, used in sports, and recently, like they also started using in ALS. Clinical, conditions. I mean, to diagnosis the clinical conditions called ALS. Okay, next. Yeah. So you can see we have 2 different types of EMG: needle, surface. Surface means we will keep the electrode like on. See, we will keep the electrode above the skin. Okay, on the skin. Sorry, on the skin, and we will take. Okay, needle means like like injections we all would have seen, and in fact had right now. So it's a small electrode they insert inside. Okay, we will collect the data, EMG. Okay, so now you tell me which one is good and which one is let's say not bad. Which one is good? Surface EMG is good. Needle EMG. Yes. Can you please explain when I'll go for needle and when I'll go for? Great, super, okay. True. Great. See, that's what I said. See, clinicians, okay. If you approach any doctors, okay, and if you are saying that like sir, I'm going to use a surface EMG to do this, okay, they will not let's say like hear, they don't want to hear the story, or else they strongly believe that okay, this will not work. You got my point. They never ever believe surface EMG. Okay, even now they are not believing. Okay, in fact, like I'll discuss, like there are some other techniques, okay, that stands in between surface and needle EMG. Sorry. Okay. Yeah. So basically, I'll so surface EMG, you see the electrode usually placed on the surface of the skin. Okay. One important one fundamental difference between these two things, let's say techniques, or if you see, the first one is non-invasive. Okay. Okay. We all can perform. We all can use this technique. Okay. We need not have to get certification from anybody else, anybody in the thing. Okay. But the second, we cannot use it. Only doctors can use. Okay, and that is widely used to what, like if they suspect any, if they want to study the conduction velocity, then they use this. They want to they want to study some, let's say, needle, some specific muscle characteristics, then they will use that. Okay, but we cannot use needle EMG. Surface EMG we can use. One important this thing is it's a non-invasive. Non-invasive means like it will not be painful. Okay, everybody can use, and we will show that in a while. So here, but apart from that, technically if we speak, see, in needle EMG we will get very good signal. Okay, because the sensor will have direct contact with the source. Okay, whereas surface EMG, you see, I keep source on the skin. Okay, and most of the signals, as I said right now, see in this case, see I mean in the figure in the top one, okay, see we are interested in biceps, okay, see biceps, I mean like whatever the contraction happens in biceps, okay, that signal should anyway propagate all the way from its origin to the electrode, okay. So in between we have fat layer, we have skin layer, and apart from that we also have an interface. So most of the signals will be lost. Okay, and this is one of the reason, like why doctors this thing, and this is also one of the reason why we are interested in taking this technique forward and like using for control purpose. Okay, next. So yeah, I'll stop with this slide. See, regular surface electrode. Okay, what we were discussing. Okay, apart from that, see these two techniques, okay, recently like I mean okay, they developed. See, uh, I mean this is surface, okay, surface electrodes, okay, these are surface electrodes. See, these are like very small electrodes, but not you see these are very small electrodes, but it comes as a array. You got my very small electrodes, but it comes as an array. Okay, so which means we will have better selectivity, okay, with this technique than this, because I have more data now. Okay, and here you see these are like what I mean this is high density EMG we call, okay, and this is high density EMG, but the transmits the data wireless, that use wireless communication for transmitting the data. Okay, so these are like nowadays like I mean widely being used. Okay, you can see this. So I mean this you can see. Okay, uh, I mean like in even like sports application and so on. Okay, we also have such a sensor. Okay, we'll be going to what like show that in a while. Okay, see, but we have this. Okay, this gives and another one very important this thing. You see, can you please go back the previous slide? No, back. See, yeah, see this one. Uh, see, I mean when we perform recording, okay, we can pinpoint the source. Okay, but here you cannot pinpoint it. Okay, can you please go to the next? Yeah, here, okay, see this is surface electrode, but still we can pinpoint at some extent. So this technique stands somewhere between the surface and needle. Okay, but again this is very costly. Okay, very costly, and only very few groups involved in designing this identity EMG. In fact, like our group, like now we are also just interested in developing like identity EMG. Okay, and it can be used for like multiple purpose. Okay, with this maybe like we have our own system. We'll explain that and we'll show the EMG, and that's and yeah, with that like we'll wind up. Okay. Uh, okay, we have that sensor. You can see that generally இங்க கொடுங்க இன்னும் 2 ஸ்டிக் கொடுங்க. See, these are the electrodes. Okay, see this is by the way this is not reusable. Okay, we can use it for only one time, and it lasts for about 45 minutes. Okay, now I mean some of my colleagues are also working in this thing. I mean extracting signals from tactile electrodes. Okay, for example, we are wearing cloths right now. Like that, we can wear the electrode and we can count the data. Okay, but see, this is again one of the conventional electrode. Okay, this is like we are having say for double check. Okay, you can see that like if you want you can feel it, you can check it. You can also just open it. You can check for other comes in like that. So, I mean, all India's any of yeah. So maybe see, this is again. See, this is our EMG system. Okay. I mean, this is two-channel EMG system. Okay, which means it could able to collect capture EMG from two sides simultaneously. Okay. So and yeah, this is a bit costly. I mean, we have 4 channels and it comes with 3 line. Okay. Okay, and this is from biobank. So we will show like I mean, how do we place the electrodes and how the signal, because like I keep saying like the signal okay looks like noise, like you can see like how it looks like and so on. Yeah. How do you you can அங்க இருக்கு பாருங்களேன் மசில் சென்டர்ல வச்சுட்டு பாருங்க, அப்புறம் கீழே வச்சு பாருங்க, இங்க வச்சிருங்க, இங்க வச்சிருங்க. You show this in all you better use at least 2 channels.
എടുത്തിട്ട് വരട്ടെ
Okay. Yeah. See, we have placed a sensor. We have placed a sensor. Okay. See, this is the front part. Is biceps. And the opposite side, we have triceps. So what actually we have done? We placed electrode, okay, two electrodes. Yeah, then we have you see like we attach this attachment. Okay, so here two electrodes. Back side on triceps we have attached the. So what actually we are interested in here? See, when we perform movement, let's say like see, when I want to do my, let's say, when I want to flex my see, okay, hand, okay, see, the biceps muscle will be contracting. Yeah. See, at the same time, on the other side, if we see triceps will be extending. Okay, one muscle will just shrink. At the same time, other muscle will be, let's say, one muscle will be shortening. At the same time, other muscle will be lengthening. Okay, so whenever muscle contracts, okay, you will see burst. Okay, compared to the other, see, biceps will be contracted, started. You will see very nice signal. But this thing, triceps, see, when it contracts, suppose it has to extend. Okay, and when I move my original, let's say my actual state, okay, my triceps will be in the normal, will come to the normal. Similarly, biceps also comes to the normal. Okay? So we call this as agonist muscle, okay, and this is antagonist. Just suppose you think about what happens when we don't have triceps muscle. See, the triceps muscle, we are not having. When we try to flex the this thing, and when I flex, okay, see, I cannot flex. I cannot able to flex like I can flex only up to this level. Then I cannot go again like say, when goes because the other side it will be lengthening and it reaches its maximum, let's say, length. It cannot go beyond that. So this control will be given by, will be provided by triceps. Okay, this orders. The other side lengthens. So we can this thing flux only till the maximum length when only till the thing triceps goes to its maximum. So against antagonist, you can see the activity, muscle activity here. You can see this. See, you see this phenomena here. Okay. See, one muscle is contracted. Okay, and you see the amplitude of EMG. Okay, we will come to the frequency. Okay. By the way, if you take, let's say if I am giving a signal, okay, what are all the important parameters we see in this? Let's say I am giving a signal to you. Okay, and I want you to I want you to characterize the signal. What are all the features or parameter you look for? Frequency, amplitude. Frequency, amplitude, time, length, time, length. One thing we all studied in our Pace. 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 And this is time. Or very much. You might have, I mean, those who studied Fourier transform might have recollect. Okay? Time delay corresponds to phase shift, and phase shift corresponds to time. Okay. So here, generally, like this EMG, I mean, this thing, I mean, the top one is associated with the biceps. The bottom one is associated with the triceps. Okay, and we see more activity in biceps, and comparatively less activity. Okay, see the same. Okay, happens. See, for example, when we walk, we have our thigh muscles, quad and hamstring. Okay, you see every time we walk, the gait. Whenever like we flex our knee. Okay, you see the what like the this thing I mean the quad is quad is starting of the knee. Quad is lengthening. Okay, your hamstring is starting. Okay, similarly when you extend your knee, okay, the biceps starts. Why I am saying this? Okay, for example, let's say patient have this thing. I mean, patients, let's say, like with ebony amputee. Ebony amputee means they will not have joints. For some reasons, okay, they remove their joints. Okay, they have only thigh. Okay, now let's say we want to come up with this thing. Okay, in fact, like we have Jaipur foot, but Jaipur foot is like it provides only support. Okay, not in regaining the movement. Okay, now let's say we want to use EMG because we have anyway we have see this hamstring and quadricep plays a key role in actuating the knee joint. But I have my muscle, but I don't have my joint. Now I have to come up with my prosthetic knee, and this prosthetic knee should be driven by the signals that are like collected from your hamstring and quadriceps. Now I am going to do this. Which one is what agonist and which one is antagonist, and how the signal characteristic changes. Okay, and if I see any pattern, and if that is reliable, then I can use that, and I can just help my patient to regain to restart the movements. Okay, see for example we have Jaipur student, I mean, I mean, okay, anyway we have this okay. See, anyway, we will discuss. See, Indian government I mean, like we have this thing. Like Indian government gives Jaipur food for those who lost their limb. I mean, that food is called Jaipur. They helps in only it provides only support. Okay, and by the way, if you look at the energy expenditure, okay, they have to spend 5 times more energy than us for every single step, which means, okay, the energy we spend for 5 steps, they have to spend that much energy for every single step. Okay, now let's say like with EMG they able to restore the movement, then I can use I can select some motor. Okay, and this EMG information given to motor, and this motor can now can actuate the knee. Yeah, I mean knee joint. So in that way, somehow like will help them to bring, I mean to minimize the energy expenditure. So that's one of the research that is happening. So yeah, with this we'll stop here today, and maybe the next class, I mean tomorrow.